In this video, we want to derive the work energy theorem for a rigid body. So we've previously shown that the kinetic energy of a rigid body is equal to half mvc dot vc plus half hc dot omega. To calculate the work energy theorem, I will start by taking the derivative of this expression. The derivative of the kinetic energy with respect to time, T dot is equal to half m Vc dot Vc, that's the product rule here, Vc dot Vc dot, okay, plus half Hc dot omega plus half Hc dot omega. Cool. So then these first two terms, these add up to half. Well, the half goes away. Half plus half becomes 1. M AC dot VC. And we know from the balance of a new momentum that the mass times the acceleration of the center of mass is equal to the sum of forces acting on the system. So this term becomes equal to, all of it, that's equal to the mass or the sum of force acting on the system F dot VC. Which is cool. That's the first expression I have here in this form of the expression of the kinetic energy. So then I still need to figure out what this part simplifies to. Oh, I forgot my dot here. Omega dot. So let us see what this omega dot is actually. Omega dot is alpha. The derivative of the angular velocity is the angular acceleration. Now that's the derivative of the angular velocity. Remember the expression for the angular velocity, omega x ex plus omega y ey plus omega z ez. Okay, that's omega dot ex plus omega dot y ey plus omega dot z ez plus the derivatives of the basis vectors, that's the rotational basis, so the derivatives of ex, ey, ez are non-zero. Omega x ex dot plus omega y ey dot plus omega z ez dot. Now remember, what are omega ex dot, ey dot, and ez dot equal to? These are just equal to omega cross ex, omega cross ey, omega cross ez. Easy. So that whole expression over here, that's equal to omega cross, well, omega. And we know that's going to be equal to 0. So this whole term goes away. Alpha is just equal to omega dot x ex plus omega dot y ey plus omega dot z ez. You might write that as the co-rotational rate of omega, the derivative of omega keeping the co-rotational basis fixed. Okay, cool. And then you can show by direct calculation that h dot omega is equal to h dot omega dot or dot alpha. So that you show that just by direct calculation. So you have to calculate the expression of hc, put that in there. That's gonna be I xx omega x ex. Well, I'll take ex as a common factor. Okay, plus I xy omega y plus I xz omega z c ex plus the whole expression along ey plus the whole expression along ez, and keeping in mind that the products of inertia, these are constants. What changes in time are the components of the angular velocity and the rotational basis factors that you can show from direct calculation this equivalence. So if I go back to my expression for the kinetic energy, that's just equal to also h dot c dot omega. Because this term, that's equal to half h dot c dot omega. Okay, so now my kinetic energy, I can write it as equal to F dot Vc plus, well, what is H dot C? That's just the sum of moments about C. Remember the balance of angular momentum of the center of mass, MC, is equal to H dot C plus MC dot omega. Okay, and that's T dot our work energy theorem. That's the derivative form. If I integrate with respect to time, I will get that TB minus TA is equal to the integral from TA to TB of F dot Vc dt, the sum of the force acting on the system, that's acting on this, now equivalently acting on the center of mass, dotted with the velocity of the center of mass, plus the work of a moment, that's a new concept, that's just equal to the integral of the moment times dotted with the angular velocity of the body dt. Cool. Now, the form of the work energy theorem that we're going to use most frequently is not this one. It's going to be another one, which is our friend over here. So then how do we get this form? I will start with figuring out what F is and what the sum of moments about the center of mass are. Okay, so here, F is the sum of forces acting on the body, so that's equal to the sum of the individual forces. And then the sum of moments about the center of mass, that's the couples, plus the moments of all the forces about the center of mass, the sum of I minus RC cross Fi. Okay, so then I will plug these two expressions into this one. So T dot, the rate of change of the kinetic energy, is now the sum of Fi dotted with Vc plus the sum of Ri minus Rc crossed with Fi plus the Me, okay, dotted with omega. The sum goes from I equals 1 to n, where n is the number of the discrete forces Fi acting on the system. Okay, and now omega and Vc, I can put them back inside the sum because the sum does not depend on them, plus the sum of Ri minus Rc crossed with Fi dotted with omega plus Me dot with omega. Cool. Very well. This I can rearrange. I can write this as Fi dotted with omega cross Ri minus Rc. Okay, that's because if I have A dot B cross C, a scalar triple product, that's what we call it. It's cyclical basically. I can prove that I can write this as B dot C cross A, which is equal to C dot with A cross V. Okay, so now looking at these two terms, these two sums, I can take Fi as a common factor. So that's the sum of Fi dotted with Vc plus omega cross Ri minus Rc. Okay, cool, plus Me dot omega, that's outside the sum. And what is Vc plus omega cross Ri minus Rc? That's just equal to Vi. So then that's sum is equal to Fi dot Vi plus Me dot omega. Ta-da! We got this. So then the derivative of the kinetic energy can be written as the sum of Fi dot Vi plus Me dot omega. And again, I can integrate this with respect to time to get that Tb minus Ta, the kinetic energies at time B and A, respectively are equal to the integral, the sum of the integral of Fi dot Vi dt, Ta to Tb, plus the integral Ta to Tb, Me dot omega. That's just the work of the couple from A to B. And that's just the sum of the works of the individual forces Fi from A to B. Again, remember that to calculate the work of the force without the force with the velocity, Vi of its point of application. That's very important. Okay, and that's it for this derivation. Thank you.